Alright, I think that we're not going to get a huge number more people. Sorry, I'll just quickly turn off the sound off the stream so I don't get distracted. Okay, so I guess welcome to dynamic programming. A very interesting name for a fairly difficult concept to start with, but hopefully after today it should be a lot easier. Alright, so I guess we'll start with what is DP. So dynamic programming in a sense is a name that means literally nothing. When Richard E. Bellman was working at the time, he needed an umbrella term for all of his work. And at the time, the people he was working under were really averse to research. And so he needed a term that could not be used as a pejorative or in a pejorative sense. And the term that he ended up coming up with was dynamic. And what he was doing was really umbrellaed by the term programming, and such dynamic programming was born. But what actually dynamic programming is, it's basically better surmised as DAG programming. So what it does is it takes a recursive function and memorizes results for that recursive function such that instead of having an exponential amount of time to complete that particular recursive function, it'll take an order of polynomial time. Yeah, so this is a really important concept, and pretty much all the time, every single contest has at least one DP question, unless you're doing some very, very easy contests. So for now, we'll forget what DP is. What's really important before we even start on DP is what is recursion and examples of recursion. So we'll start with the problem where we have a DAG. So this DAG is weighted, and we want to find the maximum weighted path given a source and a destination. So this sounds really similar to Dijkstra's when you first look at it. It just sounds like an inverse of Dijkstra's where we look for the heaviest instead of the minimal. However, we run into the same problem with Dijkstra's where if you try and take negative edge weights with Dijkstra's, sorry, if you have to handle negative weights with Dijkstra's, suddenly it breaks down because it doesn't know, it might not have taken into account an edge that was actually decreasing the minimum further. So if you're trying to find maximum with positive integers, you run into the same problem. It would be fine if we were trying to find maximum with negative integers, but that's just that is the literal inverse of Dijkstra's. So Dijkstra's is not going to work for this. So what are we going to do? Well, the other alternative is we can just look at every single path. So this is obviously very slow, but let's explore that for a bit. So we can define a function. I'll actually bring up the board for now, sorry. That is not it. Okay, so say we have a DAG. We'll draw a very, very simple DAG. So we have 4 nodes. We'll label them 1, 2, 3, 4. And I'll just draw some edges in between them. So we can draw this edge, this edge, this edge, and this edge. So a very simple DAG. These all have weights. They can be arbitrary. It doesn't really matter what they are. So, well, it does for the computation, but for demonstration purposes, these can all be the same. These can all be different. It doesn't really matter. Because what we're trying to do is find a way that we can enumerate over all these possible paths. Say our source is 1, so this node, and our destination is 4. The best way that we can enumerate across all these paths is for every single node, we travel down each of its edges and compute the maximum path from whatever node it reaches. And obviously if it reaches the destination, we return 0. So what's the best way of writing this? Well, we can actually define a recursive function that takes in a node enumerates across all of its edges and returns that value. We define that by the following code sample. So we define a function called longest path. First of all, we look whether the path is the destination. So that would be whether it was the 4 or not. If so, then you have no more maximum path that you can go from there. So you return 0. Otherwise, you set your return value to be 0 because if your node doesn't have any children, it would also be the case that your longest path would be 0. Then you enumerate across all your edges. So your edges will have two components. They'll have the node that they're connected to, and they'll have the weight. So that's in this code snippet, it's represented the child as the node and the weight as the weight of the edge. So then your return value will basically be the maximum out of the current return value and that longest path of the child plus the weight. So for instance, if I had, I'll draw out the DAG again. So I'll only draw out the nodes this time, I won't draw out the edges. But say I computed for longest path of 4. That this was, well, this has to be 0, but okay, bad number. Say it was the longest path of 3 was 2, regardless of connections. And then I knew that I knew that the only two connections for 2 were to 3 and to 4. So then I'd enumerate across those two edges. So I compute longest path for 3, which I already know is 2, and I compute longest path for 4, which is 0, and I'd return that to 2. Now, I've actually gone a little bit ahead here and sort of alluded to the way that we actually speed this up. Because right now, if we call this function is being called on itself multiple times. And we know that if we call a function of itself multiple times, that's going to end up with an exponential time complexity. So you can imagine if you have to do 2 things in your function, then you have to do another 2 things in the calls to the function. It ends up being exponential in the fact that it's multiplicative by a geometric factor of 2. So that's how the every possible path solution works. However, there is a clever way that we can speed this up. And that's through, first of all, understanding that every DAG has a topological sort. So every DAG has a way which you can order the vertices so that you're always enumerating such that all the nodes that come afterwards are dependencies. So for instance, E is, for instance, in the slides here, we have E has the children C and F, or another way to put it in dynamic programming is they have the dependencies C and F. D has the dependencies C and B. C has no dependencies. B has the dependencies A, has dependency A, and A has the dependency F, and F has no dependencies. So we end up with this topological sort, as can be seen. And there's an interesting way that we can actually exploit that for dynamic programming. If we compute things in such a way so that we can rely on already pre-computed values from these dependencies, we can actually end up computing this in, we have now a runtime of how many things we need to store. So in this case, it will be how many vertices we actually need to compute. So this can change for various different problems involving dynamic programming, but the central idea to all of it is that we're computing dependencies and then using those dependencies to compute further up the DAG. So if you can draw any problem as a DAG, with dependencies, or express it as a recursive function, because both of them are, express it as a recursive function without cycles, because both of those are interchangeable, then you'll be able to create a DP solution out of this. So yeah, so the central idea of all of this is something called memoization. So I'll just leave that in the corner because this is pretty much the entirety of dynamic programming. And all memoization is we remember solutions to previous problems. And these previous problems are always going to be dependencies in our DAG, and are often referred to as subproblems. So, quote unquote, subproblems. Sorry, I'm aware that I'm kind of exiting off screen. All right. Cool. So let's just step along a DAG, and if we're now doing it in the sense that we're doing it in the order of the topological sort, and we're storing the values at those nodes, what does this look like? Okay, so if we go to 6 now, 6 is our destination node, so we're not actually going to do anything, like we just immediately return 0. So we just enter the first line of code and we return 0. So we enter 0 into 6. Now our next node in the topological sort will be 5. So what's the longest path from 5 to 6? Well, we enumerate across all its edges, and we've already stored the result for 6. So we know the return value is going to be the weight from 5 to 6 plus the longest path at 6, which is 0. So we're just going to store 5 at 5. All right, now the next component of our topological sort will be 4. So we're going backwards in the topological sort. I'm not sure if I outlined that clearly, but whenever we do the topological sort, we always solve the dependencies first so that we can backtrack up the higher level to the solution. So again, we iterate across all the edges of 4. There is only one edge, which is 7. So then we do, so our return value will be 7 plus the longest value, the maximum path at 5, which we already computed to be 5. So that's going to be just 12. So we store 12 in that node. All right, now we end up with the case where it's not quite so easy. We do actually have to do multiple iterations. So if we go to 3 now, and we iterate across all of its edges, we find that we either have 2 plus 5, because the weight of 2 plus the already calculated value at 5 gives the longest path if you go down that path. Or if you go down the path from 3 to 4 to 5, we end up with minus 3, which is the weight from 3 to 4, plus 12, which is the stored value at node 4. So minus 3 plus 12 is 9, 2 plus 5 is 7, so we take the maximum of those two and we store 9 in 3. And then again, we use the same process until we get to the top, and we find that our solution will be 11. So how much faster was that? Well, we only ever had to look at an edge once, because we memoized the solution of what would be the path using that one edge. So although we actually used edges multiple times effectively, we only ever had to calculate using the edge once. Cool. So this is all good fun, but in order to do this, we had to have a topological sort, and we had to reverse that topological sort. So how do we actually do this? Well, naively, we can actually just execute the function. If we execute this recursive function, the way recursion works is it builds a stack, And so as you travel down that stack, you get to the bottom before you're actually computing values. So once you get to the bottom dependencies, you're actually computing the bottom dependencies first. And so yeah, you create your topological sort just from drilling down to the bottom of the stack before you're actually able to solve anything. So if we look at how this works, if we execute the function, so first of all, we're just naively enumerating to this position in the graph. Like we could have chosen any of those three children available, but yeah. So so again, with a topological sort, it doesn't actually matter what order you do the final dependencies in. It just matters that they are done. So yeah, in this case, we calculate. So in this case, we'll calculate in this specific order because as we're going down in the recursive function, we're iterating across the children of each node, and we're not actually calculating anything until the bottom dependencies. So right now, this is just the first child in the node. So we then go across its children, and then we go across its children, and now we have to go back up in the stack. Now our stack is empty because there's no more children. So we calculate our value here, and then we go back up, and we calculate our value here. We go back up, we calculate the value here, and now our stack has only got one element in it. So we have to go and enumerate across the children of the root node, which is the one gray node left, as well as the destination node. So we now go to the gray node, and we can calculate its value there because we've already pre-computed the values below it. And then finally, we can calculate the root node because we've already calculated the destination. Cool. And so that's how we do a fairly simple topological sort. So how do we actually? So this is actually talking about implementing DP. So whenever we're implementing DP, whatever function that we write, you can write it really abstractly as basically if you have some function with arguments, so arg1, arg2, etc. Then you can just store that in a dictionary. You can store the results in a dictionary. So it doesn't actually matter what these arguments are. They can be numeric, they can be strings, they can be any data type you can think of. Of course, if they're strings, if they're tuples, you have other added complexity in there for the number of combinations of strings that are possible, and the number of combinations of tuples that would be possible. But you can effectively use any key to store stuff in your block of memory that you're using to memorize things. So if you call something mem, and we'll make it a dictionary, and basically at the start of every single function, every single time we call a recursive function, we want to check if our arguments are already in mem. To etc, if they're in mem, and if they are, then we want to return mem indexed by them. Sorry, I'll just make it slightly nicer. Yeah, indexed by So the actual implementation of this can be quite straightforward. So for instance, if you had two arguments here and they were both integers, then you could store it in a multi-dimensional array. If you had one argument here and it was just an integer, then you only need one dimension of the array. So for our example of the longest path, our function takes in one argument and that argument is a node. So as long as you hash that node, or well, it depends on how that node's actually represented in your implementation, but as a general thing that you can say, as long as you index your memory by that node, you can find the value that's being pre-computed. And if it's not in there, then you compute it, store it in its memory, and when it's called for use later, it's a constant time lookup. And so effectively, it's a very easy abstract way to implement DP. So what does this look like in actual code? So again, we see our mem function, our mem dictionary being used at the top. First of all, it doesn't really matter if you're checking whether it's the destination or whether it's in memory first. But in this case, it's a slightly better running time if you check node equals destination first. Actually, sorry, it would be a slightly better running time the other way around, but that's not really a huge deal. But yeah, so we check if it's the destination, we return 0, which is the same as our original algorithm. We check whether the node is already being computed, whether it's in our memoized table. If it is, then we return the value of that. Otherwise, we do the normal compute, and we store that result in mem. And that's all DP is. That's DP done. You've learned DP. There is nothing more to this aside from this idea of memoizing and what a DAG is. Now, the interesting things that come with DP are all implementation based. So right now, what I've been talking about this whole time is something called top-down DP. So top-down DP is this idea of you store the topological sort like through the recursive function essentially. Bottom-up DP is the exact same thing. However, instead of the topological sort being done by function calls, it's done manually by you before doing the DP. And there are some problems where if you do this, you have a far quicker running time just because you end up getting rid of a lot of the useless overhead of adding to the stack a lot of times and having to like trail back up the stack and such. It can just be the case that your dependencies are two values which you compute iteratively. But it does depend on the problem. Okay, so I'll talk about the benefits of both. So top-down, it's provably correct every time. But it is slower when every state has to be visited. Like we would have had a lot of computations there where we're doing things, like although we're doing things in constant time multiple times, it's still slower than doing things in constant time once, which is something that bottom-up DP enables. So bottom-up, yeah, we essentially do the topological sort manually, and then we iterate across indexes, often backwards, but sometimes they can also be done forwards. As long as you're understanding what the problem is, it doesn't really matter which way you do it. It's sometimes conceptually easier to iterate across things backwards because bottom up is quite literally we start the dependencies and we work our way up. And so our answer will often be the very first result in our memoization table. Yeah, and this idea of it can be made faster and more memory efficient. Obviously, when you have hash maps and dictionaries, or it might not even be a hash map, it might be like a C++ map where it's stored in a red-black tree. In that case, we have a lot more overhead to our runtime in general, just in terms of like not necessarily time complexity factors, but constant time factors are a lot higher. Cool. All right. Yeah, so what do you actually need to be good at DP? Well, it basically boils down to, can you get the recursive function out? Because if you can get the recursive function, it doesn't really matter if you can get the recursive function out, the memoization is trivial. The memoization will always be essentially take in the arguments into your dictionary, and if the arguments are nice, then you can use them as arrays, indices. Sorry, you can use them as array indices. Otherwise, you might need to use them in a map. But yeah, as long as you can find the recursive function, you're almost always done with DP. So uh, although although this is the case, they need to not have cycles. So it does need to be a DAG. It needs to have dependencies that it can call back on. It can't its dependencies cannot be reliant on values that haven't been computed yet. And yeah, and then you just need to memorize. So although this conceptually is not actually that difficult, when you're actually confronted with problems, it's quite difficult to see where the recursive function comes from. So to talk about that, I want to go through an example. Sorry. I guess this is just a further argument first, talking about time complexity with DP. So DP basically, its time complexity will always be it's the amount of things you need to store, because that's the amount of values you need to compute, and the average time of how long those values take to compute. So for instance, with the longest path, the average time is constant. We were storing, the average time was the number of edges over the number of nodes. And then the number of things that we were storing was the number of nodes. So complexity was actually O of number of edges, but we were also doing it over nodes, so it's O of E plus N, which is a little bit confusing, but yeah, that was essentially our complexity. Cool. So I want to go through an example right now. I'm not sure if anyone's in the chat, but if they are, I'll definitely leave this problem up for a little bit, just to see whether or not there's a recursive function that comes to mind, and if not, whether there's a recursive function that might be something that doesn't immediately do something, but might end up doing something a little bit later. So I'll leave this up for a little bit. All right. So the idea of this problem is basically defines the longest increasing subsequence for smaller and smaller sections of the array. Because if we can find the longest increasing subsequence of the array from a certain point, then we can use that as a dependency to find the longest increasing subsequence of it from the next point, and so on. And so we can create our DAG out of that. Yeah, so that's So yeah, if we define our function as it's finding the longest increasing subsequence from I to the right, then uh, then our maximum increasing subsequence will be the max of all those f of I that we calculated, yeah, for all I. Alright, so this is a function. This is how to define it recursively. So what does this mean? Basically, we look at our function if our I equals n. So if it's the length of our array, obviously in an actual string implementation, this would be so say your string was called. Sorry, I'll just bring this up. Say you had a string s. You can either store that s, you can either store that n outside of the function or just get it from this s. So you call this as s.size is the same as n essentially. So when we're saying in pseudocode that I equals n, it means that we're at the last element. So we know already that if we're at the last element, which in this case would be s.size take 1. So if I equals s.size take 1, we're already at the last element, and so there's only one subsequence that can be created, and it is an increasing subsequence because it contains only one element. It cannot be decreasing. Well, it's a non-decreasing subsequence. Then yeah, we have our solution. But again, it depends on how the question is outlined. If it's a strictly increasing subsequence, then you possibly can't use this answer. You might have to use, you might compute this as 0 and then work off of like other dependencies. So for instance, when this is 2, you know that it is either going to be 1 or 2, and you can compute that manually in the function. Cool. Oh, sorry, I didn't actually go through all of it. So the other part of it is we go through, we call the function on itself for all j that it's greater than I, so that like array I is less than j, or 0. So those are going to be, this is finding the length of our subsequence. So for any time where the function returns 1, we're going to increase it by 1. For any time it's going to return 0, we don't do anything. Because undefined is where it doesn't actually return anything. Cool. And so the way that we do this with the DP is we just store that in an array called f of I. And so whenever we've already computed that value for f, then we're already done. We don't need to do any more recursive calls. And so this is with bottom-up DP, because we've already defined the function such that if we start at n and then go to 1, we're doing it in our already pre-computed topological sort. Alright, fantastic. And we've solved it. That's O of n squared. There is an O of n log n solution, but it's not involving TPs, so we won't go through it today. But if you like, there are plenty of resources available to talk about the n log n solution, because longest increasing subsequence is a very famous problem. Cool. Alright, so let's think of another problem. If we imagine that we're at the cinema all day, there are some movies on, each start at some time and end at some time. You must watch the whole movie from start to finish, and you want to watch the maximum number of movies. How do we do this? Okay, so what are our subproblems going to be? And can we use DP? Sorry. There's actually a lot of questions here because there is a greedy solution to this that we'll go through. Actually, I'm not sure if we've been through. Greedy may have been covered already. But yeah, so this is a classic problem, which is the scheduling problem. And there is a DP solution to this. But yeah, it's basically the idea of storing all your times. Cool. All right, if we have, I think that's all I want to say on DP, honestly. Because after this idea of the bottom-up approach is just a reverse topological sort that you've encoded manually. The top-down approach is just memoizing your function calls to your recursive calls, to your recursive function. Pretty much the only other part of DP is implementation. And implementation isn't always trivial. Sometimes it is, and it's very convenient when it is. But yeah, that's essentially the case. So I might give an example of an implementation in a couple of different languages. Probably just Python and C++, just because Java, it's fine, but there's a lot of boilerplate code which can be avoided with using other languages. And hopefully, if you can understand either if there's stuff in the C++ solution that you can't understand, you should be able to understand it with Python, because yeah, Python's quite idiomatic and it's a lot of the pseudocode that I'm using. So we may go through that. So what I'm going to do is first of all solve it on the board. So it's a very simple problem, and it's the classic problem that's always used for teaching this. It's the Fibonacci sequence. So so we can define the Fibonacci sequence is very well defined recursively. So we know that abstractly, the zeroth turn of the Fibonacci sequence. Oh, sorry, my pen appears to be not doing great. So if we have fib of n, we know that the first thing in the Fibonacci sequence will be, sorry, if n equals 1. Sorry, if n equals 0, we'll start out. If n equals 0, we return 0. Because this is f0 equals 0 and f1 equals 1 and fn equals f n take 1 plus f n take 2, because that's the recursive definition of the Fibonacci sequence. So we'll do elif n, oh sorry, we actually can just do if n equals 1, we'll return 0, sorry, return 1, because that's our 1th term. Otherwise, we return fib of n take 1 plus fib of n take 2. Cool. So what are our dependencies? What does our DAG look like? What's all this look like abstractly? Well, if we draw a DAG of values for n, so we're not going to care about, we're going to label our nodes by their value n, so that's going to be our key, and the value at each node is going to be our value in the Fibonacci sequence. So for instance, if we have, so it'll always start with 0. Sorry, I'll start with labeling these with the keys. So 0, 1, 2, 3, 4, ... n. So you can't really see that very well. I'll try and draw it bigger. Cool. So 0, 1, 2, 3, 4 to n. So if we have this as our, so this is abstractly for all Fibonacci numbers. Obviously, if you have less than 4, you just decrease where n is, but it's still the same DAG. So what would our DAG's dependencies be on? Well, they'd always be on exactly 2 nodes in the DAG. So for instance, except for 0 and 1. So 0 and 1 are already pre-computed cases. So they already have they already have 0 and 1 as their values. Then 2 has 2 dependencies. 3 has 2 dependencies. 4 has 2 dependencies. Yeah. And etc. So they all have 2 dependencies. So as long as the way that we're doing DP is like drilling down into this n equals 0, n equals 1 territory before coming back up, then we can solve the problem. So naively, we can just say, all right, we'll add something called mem. We were indexing by n, which was just something in memory. So it was just, it can just be an integer index. So our mem is what, like, it'll be between 0 and 1e7, something like that. Because this is calculated in linear time, you can't expect people to run more than those operations in a second. So our mem will just be an array, and we test whether something is in the array for whether or not it's 0. If it is 0, then we go and do the computation. Otherwise, we'll just return the value. So I'll quickly share screen so that I can give an example implementation while talking through it. Just hold on for a second. Oh, apologies. Cool. All right. So if we have so I'll make something called fib in C++. All right. So I'll start off with a bunch of boilerplate code. I'll start with my DP function, so I know it's not ever going to be like bigger than, let's say, bit shift. I'll be slightly less lazy, so we'll make n to be no bigger than 1e7. So that means that we can immediately define like our memory that we're going to be using. So I'll make it an array, and then I'll make my main function very quickly. So I won't do anything for fast IO because I won't need it. So I'm just going to make a variable n, which is going to be what I'm using to call to my Fibonacci function, and then I'm going to compute n with fib_n. Now the real magic actually happens when I'm computing the Fibonacci sequence. So actually, in all fairness, this should be LL. Just so that we don't overflow. So if I do imp fib int n, this means that I'm creating the recursive call to the Fibonacci sequence with this. So again, we look, actually before I do this, just for cleanliness sake, I'm going to make a function called init, because with C++, you need to make sure that you're doing everything, you're initializing everything properly. So for instance, mem needs to be zeroed out. So we'll just do that really quick. So this sets all of mem to be 0. So now it means when we check this, we won't have garbage inside it. So if mem n equals 0, not equal to 0, we can return mem n. Else we'll do if mem, sorry. Just a second. No. I just want to make sure I don't make a silly implementation error. So if n equals 0, we'll return 0. If n equals 1, we'll return 1. And then if n less than 0, we'll return 0. I don't think that's possible, but no, it's not possible. I won't exclude it. Yeah, okay, sweet. So if mem n equals 0, is not equal to 0, then we return mem n. Otherwise, mem n is going to be fib n take 1 plus fib n take 2, and we'll return mem n. Right, so if I compile it and I run it, so now I do something like something that's verifiable first. So let's do like 4. Fourth Fibonacci term is 3. Cool. Let's do 5. It's 5. 6. It's 8. 7. It's 13. So this seems to be working fine. Let's test speed. So if we do something like 1000, normally without DP, this would take 2 to the 1000. So it should be monumentally slow, but it's instant with DP. And so that's the C++ solution. If we make the Python solution, it's going to be very, very similar. Oops. Sorry, not very used to Windows. So our Python solution is going to be pretty much the exact same. Again, not going to bother with fast IO. So we're going to have our n equals input. Actually, it's int input, sorry. We're going to have dp. Actually, sorry, we can, I guess it's Python, we can do this. dp equals 0 for in range n. Then we def fib n, and if n equals 1, sorry, it's Python, n equals 0, we'll return 0. If n equals 1, we return 1. If dp n is greater than 0, then we return dp n. Otherwise, dp n equals fib n plus fib n take 2 plus fib n take 1. Alright, cool. And then we just print fib. Oh, sorry. I technically should do this. Oh no, not technically. I definitely should do this. Clever DP, because it's Python print fib n. That should be it. Python 3 fib.py, and we'll compute again to verify it. It's 4. Oh, it's out of range. dpn. Ooh. Oh, n plus 1. Oh, sorry, and you return it. Cool. Yeah, so that's verifiably correct. And then again, we do our speed check, and that is very wrong. Sorry, I'm gonna have to take a little bit to figure out exactly what I did wrong. It's probably gonna be easier if I actually just print it. Yeah, I want to do this like, what, 20? Um, I'm really curious why it's not actually storing things in DP, or why it's not editing DP. It might just be the case that I have to do this, because Python, fib and dpn, dpn take 2, dpn take 1, return dpn. So this is just printing a reference, so it should all be fine. I get rid of this. Yeah, so now it's actually populating it properly. So we do this with 1000. That is very wrong. Oh, sorry. It's very wrong for a different reason though. Oh, sorry. Yeah, no. Of course it's like this. Because the Fibonacci numbers get like very, very big, so it's overflowing in C++. So it's actually correct in Python. My bad. Yeah. So if we look at something like this, it's already getting ridiculously large. So in C++, normally you do this modulo, like a prime, whenever you're computing very, very large numbers, and like verifying that they're correct. But I didn't. I just did long with this. So so it was overflowing long, and that was the value that it was giving. Whereas Python actually uses big integer, and so we were actually getting the correct answer. Cool. All right. I have nothing really more to say on DP, aside from some of the things that can be used as a resource for learning DP is just practice problems after practice problems. So some of the ones that are really good examples and stuff that is really critical for knowing if you're going into competitive programming. Subset sum and knapsack are very classic problems that variations of them get brought up a lot in particularly lower level programming competitions. And I don't mean lower level as in like to take anything away from them. I just mean that they're not like Div 1 code forces. They're not like CodeJam. Even CodeJam. Kickstart absolutely uses 0 on knapsack and subset sum, or any sort of subset problem. But some of the others, that are quite a lot more abstract typically don't use them as much, but they use versions of them. Minimum as traveling salesman's problem is another classic. Minimum edit distance between strings, also very good examples. And if you want the CodeJam problem, where CodeJam is a really, really good source of quite tough problems typically, the 2017 problem B for qualification is a good example. So as homework for DP, Gauss Prank is a really, really nice DP. But of course you can find many different versions of DP problems on various sites. Codeforces, if you need to, LeetCode. LeetCode has a lot of nice supplementary material to try and help you get your head around exactly what DP is. And HackerRank, CodeChef, @Coder, TopCoder. There's just so many resources out there if you really want to go and take it to another level. But yeah, so from here, hopefully you now have a good idea of exactly where you can use DP, how memoization works, and how to approach DP problems in the future. From now on, it's pretty much just about implementation. And that should be it. Thank you very much for coming. I believe next week is going to be uh, number theory from memory. So we will be going over a lot of stuff to do with the primes, a lot of stuff to do with modulo, um, and also some interesting results which we can use in competitive programming. All right. Thank you very much for coming.